In this video, we will solve compatibility problems in axial loading. First one, we have a concrete block, and this block is reinforced by 6 steel rods. You see here, inside we have 6 such steel rods. Okay, each rod has a diameter of 20 millimeter. And the question is, determine the stresses in concrete and in the steel rods if an axial load of 900 kilonewton is applied. So on the top, we apply a total force of 900, and this 900 is taken over by the concrete and by the rods, and we have to find these two stresses. Well, what is given? The elastic modulus of steel and concrete is given. Let this be my positive y direction, and I write the equilibrium sigma of y equal to 0. So I have a 900 downwards, and in each rod, the force taken over is P steel 6 times, and the total concrete section takes over P concrete. As you see, I have one equation and two unknowns. I need a compatibility equation. Well, what is that? That is the lengthening or the shortening of the concrete, and the rod should be equal. So let me write down these values. The only unknowns are the force values, the length, the elastic modulus, and the sections I already know. So when you write down the values, L goes over, that's E for the steel, that is 25 elastic modulus for concrete. This is the concrete's cross section, the total cross section minus the 6 holes for the rods, these 6 holes for the rods. And here you have the cross section of the rod and the elastic modulus of the steel. As you see, I have two equations, equation number 1 and equation number 2. And if you solve these two, so the solution is steel rod. Each rod is under a compression 21 kilonewton. Total concrete 773 kilonewton. Stresses, concrete in the stress, total load, and the total area on the concrete, that will be 8.42 megapascal is the compression stress in the concrete. One rod, the force on one rod, and the section of one rod, the steel rods take over, each of them have 67.3 megapascal compressive stress. Next question. You see you have two pipes. These are made from the same material, and in the middle I apply a force P. And you have here supports on both sides. At the beginning there was no force, but if you apply this force P, you see a support force Fb and a support force Fd must be acting. So the cross-sectional area of BC is A. BC is this part. The cross-section is A. CD is over here, the cross section is 2A. Determine the support forces in B and D. And for the material, the elastic modulus is given as 25 gigapascals. Okay, equilibrium. Well, let this be the positive x. So I have FB and, FB and FD, FB plus FD minus F minus P equals to 0, one equation. Well, we have solved a similar problem saying that the delta, that is the lengthening in region 1, should be equal to the shortening in region 2. Region 1 is under tension and region 2 is under compression. Compatibility. Well, this time I'm going to use kind of superposition technique. So I'm going to take point B, and this point B will be displaced by delta P due to the force P. When you apply the force P, then only shortening in the second region will be active. Here, there are no forces, and the displacement of point B to the right is, as you see, P. Length is L over 2, that is this region. 2A, in this case, first region A, 2A is the section in the second region. That is what we call delta P. Now, we have another force, which is FB. FB is all applied directly in point P, and so we will have a displacement in the first and the second region. So as you see, FB times L over 2, first region is the area, and the second region, now the section is 2 times A, and the total displacement to the left, that's negative, is delta B. So, since B will remain at the same point after this deformation, so I can make their sum and put it equal to 0, and I find a second equation. That was my first equation. When you solve these two equations, you see that FB is P over 3 and FD is 2/3 P. Next, an aluminum pipe is reinforced with a brass core. Inside I have brass, and outside I have an aluminum pipe. On the top there is a rigid cap, okay, and on the rigid cap a force of 45 kilonewton is applied. Find the stress in both materials, in brass and aluminum. Very easy. You apply 45 kilonewton, and that 45 is taken over by the aluminum pipe and the bronze rod, and that is my equilibrium. But one equation and two unknowns. Compatibility. So both aluminum and brass should be shortened at the same level. So I write down the delta values using the forces, the areas, and the elastic moduli, and then I have a second equation. The first equation, second equation, and two unknowns. When you put down the numerical values, you find that F aluminum is 2 times F brass, and their total is, as you see over here, 45. Aluminum takes over 30, and brass only 15. In order to find the average stresses, the force on aluminum pipe, the cross-section of aluminum pipe, outer radius, inner radius, the calculation gives 5.09. For brass, force divided by the area gives you 7.64. So in the middle I have a stress of 764 on the pipe 509. In this video we solved 3 compatibility problems, and thank you for listening.